In this part, we will present a few different concepts towards how we can solve the equation of the sustainable materials by design. My name is Janez Zavasnik and I'm a researcher at the Josef Stefan Institute, and with my colleague Alexandre Nominé from University of Lorraine, we will present a solution to the raw material equation. There are several different concepts how we can address our dependency on the raw materials production. First one, not very well accepted, is the reduce the overconsumption. As we can see from this graph, the CO2 that we are emitting is directly related to the quality and length of our life. It is continuously increasing since the 1990s and increased almost for 2 times up to today with the free short-term reductions. One such example would be the dissolution of the Soviet Union in the 90s, the financial crisis in 2008, and more recently the COVID epidemic that stopped our lives. But this reduction in the CO2 were only short-lived. They have an immediate and substantial effect, but they are very hard to maintain over a longer period of time, and with a further reduction in GDP, we risk the social unrest. But we can stop bad practices like using short-lived product, overconsumption, and with the right to repair things, we can extend their lifetime. The second concept would be recycling. With the recycling, we can significantly reduce the CO2 that's being emitted in the primary production of the metals. For instance, the carbon footprint can be divided from 3 to 6 times for abundant materials such as iron and aluminum, and up to 10 to 15 times for precious metals such as gold or platinum. But with the recycling, we often lose our access to the byproducts which were already extracted during the primary production. So the third concept is a substitution, but the material that we intend to use as a substitute should save CO2 compared to the original material, should be affordable, should be equal or outperforming the existing ones, should be abundant, and should not be produced or originating in non-democratic countries. Unfortunately, the solution to this equation is often none. And there is no direct way how to find the materials that can substitute the existing ones.
So let's see now how to discover new materials that would fulfill all these criteria. To do so, we need to explore and discover new materials with high performance. But we have no time to waste, and the space is huge. Therefore, even at the beginning, at the low technological readiness level, that means at the research level, we need to assess the sustainability of materials. But first of all, let's have a look how big is the library of materials. How many materials do we know? There are different tools to find them. The first one has been developed at the University of Cambridge by Professor Jacqueline Cole. It is called Chem Data Extractor. It works a bit like a very well-known tools for generative artificial intelligence and natural language processing. So this program will read hundreds of thousands of scientific papers and extract the useful knowledge. Taking as an example the semiconductors, this software has read more than 100,000 papers and found 7,000 semiconductors. This is a huge amount. Another strategy consists in using relatively complex theoretical models and to run them on very powerful computers. In this example, 658,000 new materials have been investigated. More recently, artificial intelligence has been used to predict materials. And in this paper, 2.2 million new materials have been reported, and 48,000 most interesting candidates have been identified. It sounds like a lot of materials, but let's do a very simple calculation. Metallurgy is 5,000 years old, and it has always consisted in mixing metals. You can mix 1, 2, 3. In a steel, it's not rare to have 10 elements. You can mix them in different composition. And think about the number of combination of metals you can do. By mixing 10 elements in an equal proportion, you have 10 to the power 12 composition possible. That's 1,000 billion. It's comparable to the number of galaxies in the universe. But metallurgy, it's not only mixing metals in the same composition. We can fine-tune the composition, percent by percent, sometimes even more accurately. And the number of combinations possible of 10 metals with 1% compositional step gives to an enormous number that overcomes 10 to the power 24, which is the number of stars in the universe. So how can we now work with that? What can we do with it? Well, now in our era, and it was not the case 10 years ago, we have access to absolutely large database, which can be thousands to millions to even billions of materials. We cannot reasonably fabricate all of them and explore all of them. It's a bit like looking at the life on the universe. We cannot explore every planet of the universe. That would take too much time, and that would be too expensive. We have to select the most interesting candidate. How can we do that? Starting from the big database, we can first have an interesting question. How much materials can be produced? So then you can see that if your application, for example, requires a production of 10,000 of tons, many materials cannot be used because many materials are not produced at that level. If you remember, that is, for example, the case of the metals like platinum, osmium, rhenium. All those ones are not suitable for large production. You will eliminate a lot of possible candidates by this way. Another way to select your materials could be to avoid the involvement of any toxic materials, for example, mercury or cadmium. You can then apply any other filter. You can select a maximum CO2 emission, a maximum price, or environmental social risk that you do not want to take. And that will give you a subset of 10 to 20 materials that you can fabricate and test. This is a good practice that should now go into research for the discovery of new materials, and so that we do not waste time. Let's come now to our conclusions. First important take-home message is that there is no competition between reducing overconsumption or recycling or substituting. All of them must be run at the same time because all of them will have a significant contribution, but none of them is sufficient alone. I hope you understand now that material science is only at its infancy. It's maybe a 5,000 years old science. We know only a very small part of the universe of materials. And we have to explore it, because within that universe, there are some very interesting materials that could contribute to solve the raw materials equation. But to find them, we have to rethink our way to do materials research and to explore the field of materials. And for that, sustainability should become the core parameter in material selection. Thanks for learning with us.